This meeting is being recorded.
Sorry, what? Anyway, welcome everyone to the 121st meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Devarshi Mukherjee from Munster, and he'll be talking to us about rigid categories in functional analysis.
Great, thanks for the introduction and thanks for inviting me to this seminar. I've attended it a few times but never gave a talk here. Okay, so what I'll talk about is a class of categories which kind of naturally show up in functional analysis. And yeah, before anything, this is all joint and ongoing work with Jack Kelly. So yeah, the broad goal is as follows. I'm going to describe a class of categories which will, of course, be stable infinity categories, so sort of a shadow of a triangulated category. Therefore, it's justified that I was invited.
This meeting is being recorded.
Are you frozen or am I frozen?
Oh, am I frozen?
I didn't hear anything in the last 10 seconds.
Oh, really? But can you hear me now?
Yeah.
Oh, okay. No, I don't think I said anything. So I was just
Okay.
writing down what I
Okay.
said. Okay, so yeah, I'm going to describe this class of categories with certain finiteness properties, and these finiteness properties should be similar to finiteness properties in functional analysis. Okay, so that's a broad goal. And let me say a few words about what motivates this goal. So again, the broad motivation is to sort of transport concepts in operator algebras or non-commutative geometry to, well, in some sense, to categorify these concepts. So to transport them into the world of stable infinity categories. And let me draw some analogies which I'd like to add to in the course of this talk. So maybe on the left-hand side, kind of the most basic object which shows up is a commutative C-star algebra, which is continuous functions on a locally compact space. And this should be thought of as analogous to sheaves on a locally compact Hausdorff space with values in any stable target, but in particular, one can just take the derived category of complex numbers. So that's any commutative C-star algebra or any classical geometric object. What about non-commutative C-star algebras? So if A is some non-commutative C-star algebra, then, well, there is an ongoing program to kind of interpret these as dualizable categories. And I will talk about what that means. Okay, and kind of pursuing this analogy further, the primordial invariance of operator algebras or C-star algebras or more generally bornological algebras is K-theory, or rather topological K-theory. And this goes from C-star algebras to spectra. And on this side, you have algebraic K-theory, which goes from the category of dualizable categories to spectra. And then one can talk about the universal such invariant, and that's bivariant K theory, which is a certain triangulated category, and it's the universal one. It's the universal receptacle of any functor satisfying homotopy invariance, split excision, and compact stability. And on this side, you have the universal localizing invariant, which goes from dualizable categories to non-commutative motives. So you should think of non-commutative motives and KK theory as kind of analogous objects. And my talk will be about finiteness properties. So what's a finiteness property in the realm of functional analysis? That's nuclearity. And the analogous concept here would be rigid categories. So that's the broad layout of the talk. And well, so this is nuclearity not in the sense of C-star algebras, but rather for topological vector spaces. But actually, I will not talk about topological vector spaces explicitly, but rather embed this in a larger category called bornological vector spaces. And there are many reasons why one might want to do that. One reason being that the category of topological abelian groups is not such a great category in terms of homological algebra. So, in particular, it does not give you a well behaved derived category. And the way to remedy that is either by working in this bornological world or in the world of condensed math, but I'll stick to bornological spaces. And most things that I will talk about today has an analog in the condensed world. Okay, so I don't expect you to know what bonologies are. So I'm just going to give you a 10-minute introduction to bonological functional analysis. Okay, so what is bonological analysis? The idea is that you start with a complex, let's say complex bonological analysis. So over C. So you start with some complex vector space, and you, in a sense, forget the topology and instead consider a different structure, namely a structure of supports or bonologies. So what do I mean by that? A bonology on a vector space is a collection of bounded subsets and by bounded, I really mean a subset of the power set satisfying certain natural axioms. So, what are these axioms? Let me denote the class of bounded subsets by B of x. So, okay, the precise definition changes depending on which field you're working over, but there's something that's common to all of them, which is if S and T are in this class, then the union is in this class, then finite sets are bounded if you have some containment like this, then S belongs to this class. And the disked hull of a bounded set is bounded. Okay, so these are just the axioms of bonologies. And this pair of X with this collection is called a bornological vector space. Okay, and the point is if you're not used to thinking about sets with bonologies, then there's a natural way to go from this world to the world of topological vector spaces. And let me describe how that goes. So if you're given some bounded disk, you can, so let's call this a disk. Then you can naturally associate to this a semi-norm, which is defined as follows. So you just take the scalings of this guy, and this takes any x to the smallest rescaling such that x lies inside this bounded set. And this pair defines a semi-norm or a semi-normed space. Okay, and if for each s, x of s is a Banach space, then we call x bx a complete monological space. Okay, and sort of the way I've set this up, there's a natural functor from the category of all complete monological spaces to the category of inductive systems of complex Banach spaces, which takes the complete monological space to the formal colimit of all bounded disks and these semi-normed spaces. So the way to think about a complete monological space is by describing these, or it's through filtered colimits of Banach spaces. And this functor that I just described is fully faithful. Its essential image is what I just said, the strict inductive systems of Banach spaces, that is, filtered unions of Banach spaces. So you can really think of this as the same thing as complete monological spaces. Okay, so if you've never seen a monological vector space before, you should just think of these as unions of Banach spaces. Okay, let's move on. Okay, so before I say anything further, let me give you some examples. So, of course, almost by definition, if X is itself a Banach space, with the norm bonology, that is the that is B of X consists of rescalings of unit ball, or rescalings of the unit ball. So that is balls centered at different R's. Is a complete monological space. So in other words, any Banach space canonically gives you a complete monological space. But of course, you don't need the explicit bonology to see this, because I just describe complete bonological spaces as filtered unions of Banach spaces. But maybe the more interesting bonology is if, let's say, you have a Fréchet space or a locally convex topological vector space, then the collection of pre-compact subsets is a bonology.
Devarshi, can I ask a very stupid question? At the start, when you were talking about like being able to do homological algebra with topological groups, you mentioned that obviously one can look at Conde-Ab, the Clausen-Scholze, in the Clausen-Scholze world. So I don't know much about Bornologies, obviously. I mean, is there a connection between the two worlds?
Yes, and I will come to the connection shortly.
Okay.
Okay, so yeah, let me describe the properties of this category that I've just defined. The first property, well, I at the start said that topological abelian groups is not the right place to do homological algebra. The question is whether complete monological spaces is the right place to do homological algebra, or one right place to do homological algebra. The answer is yes. So the category of complete monological spaces and the category of inductive systems of Banach spaces both are quasi-abelian categories. And furthermore, the category of inductive systems has a class of compact projective generators. And the compact projectives are given by L1 spaces. Well, so at this point, one remark I can make already is that if you do things the Clausen-Schulze way, then kind of it all boils down to what the compact projectives are. And in their case, the compact projectives are measure spaces, which are maybe morally like L infinity spaces. And in our case, these are just L1 spaces. Okay. Right. So these are quasi-abelian categories. So you can take the derived categories, and the derived categories are well behaved in the sense that they admit a calculus of fractions and so on. And the derived category also does not see the difference between bornological spaces and inductive systems of Banach spaces. So you basically get for free that the derived categories have are compactly generated stable infinity categories. And let me denote both of them by this D of C to shorten notation. Are compactly generated stable infinity categories. And it's not just that they are compactly generated stable infinity categories, they also have kind of nice T structures. So they have right complete T structure And the tensor product of projectives is projective, so it's a projectively monoidal category. And all these things put together gives you a class of categories which are called derived algebraic contexts. And the point is that these are, so a derived algebraic context is essentially a context for derived algebraic geometry. And I suppose what I mean by that is you can now take kind of commutative algebra objects in D of C. And this essentially behaves the same way as commutative differential graded algebras would behave. But now, because we're working in this kind of analytic category, these are DG algebras, CDGAs, with topologies. And what that gives you is a natural model to do, well, a natural model for quasi-coherent sheaves in analytic geometry. Derived analytic geometry. Okay, so maybe that's a remark. Okay, so it gives you a category with nice properties. Right, so that was a brief introduction to bornological analysis. Now let's talk about nuclearity. Okay, now, well, one reason why one might even want to talk about nuclearity is that if you're interested in doing K theory, then you kind of, if you start with, let's say, the category of rings, then the way you prove any sort of descent property is by embedding rings into the category of small idempotent complete stable infinity categories. And the way you embed rings into this category is by taking perfect complexes. And what are perfect complexes? These are the compact objects in the derived category of some ring. So you now want something similar in this analytic realm. And notice that you can't just work with the derived category of complex numbers or modules over the derived category of complex numbers, because that's too large and therefore you would have Eilenberg swindle. So one needs a suitable subcategory of mod A DC that is, well, on the one hand, small enough, and two, still informative, still functional, analytically informative. And that takes you to this realm of nuclear bornological vector spaces. So now let me give a definition. A bornological vector space is nuclear if for all Banach spaces we have the following. So there is a canonical map from the dual of any Banach space tensored with X to the internal hom of Y to X. And you call a bornological vector space nuclear if this map is an equivalence. Of course, this definition makes sense in any symmetric monoidal category. But it's sort of a natural concept in functional analysis due to Grothendieck. Okay, so an equivalent way of writing this condition is as follows. For any bounded set, there exists a larger bounded set. So this contains this, such that the associated Banach spaces, or the map between the associated Banach spaces, is trace class. And what that means is that as a linear operator, if you take its singular values, then the singular values are summable. Okay, so that's what a nuclear monological vector space is. Why do I call it a finiteness property? So to begin with, if you take a Banach space with this norm bonology that I mentioned above, is nuclear if and only if it is finite dimensional. Another example is something which shows up in analytic geometry. So if you take, let's say, the algebra of overconvergent power series, which is defined as the following inductive limit, where each of these is a disk algebra. So this is defined as the following power series. And these are called complex dagger algebras. Which is a fundamental object in complex analytic geometry. And this is a nuclear bornological vector space. And the way to see this is that, well, I've already written it as an inductive limit of Banach spaces. One would need to check that for any R prime greater than R, the map from, well, the map between these disk algebras by restriction is trace class. And this is something we've done, and it's easy to see actually. Okay, so this is, these are two examples one should have in mind. One is kind of that Banach spaces are almost never nuclear, and they're nuclear if and only if they're finite dimensional. And the other is a dagger algebra. Okay, now I'll now talk about a construction which kind of starts with any complete bornological vector space and spits out a nuclear bornological vector space. So in other words, we are going to force this property. So what do I mean by this? So again, let X be a complete bornological vector space. What we define is then a bornology where a subset is bounded if and only if there exists an increasing sequence of bounded subsets, where all of these are in B of X, such that the associated maps of Banach spaces is trace class. So we just take the bonology generated by such things. Then pretty much by construction, X, Bx nuclear, which I'll just shorten to X nuclear, is a nuclear bornological space. Okay. And what I just did was the universal way to take a bornological vector space and spit out a nuclear bornological space. Or more categorically, we just defined a functor from C-born to C-born. That lands inside nuclear bornological vector spaces and exhibits nuke C as a co-reflective
Hi, I have another very basic question. I don't know if you like covered this when you first introduced nuclear spaces. Are these connected to what Efimov calls nuclear?
Yeah, I'll come to all of that. So
Okay,
right
so-
now I'm talking about the classical
Yeah,
notion of
okay.
a nuclear bornological vector space. I'm sort of setting it up in functional analysis land, and then through a construction that I'll come to in like 2 minutes.
Okay.
This will be very similar to what Efimov calls nuclear. Okay, so the point is we have this junction of nuclear and complete bornological spaces where this functor is right adjoint to the inclusion. Okay. Right. So now let's talk about it from the point of view of derived categories. So this functor, nuke, is to begin with, well, I guess I should call this a lemma. So this functor is exact and projectively monoidal. No, not projectively monoidal, just monoidal. So we get an induced functor from D of C to D of C, which factors through nuke of D of C, where these are the nuclear objects in the derived category of complete bornological vector spaces. Okay. And a lemma, which essentially follows from Scholz's notes on complex analytic geometry, nuke of DC is the end of basic nuclear objects. Say what that is. Basic nuclear objects are sequential colimits of trace class maps of chain complexes of Banach spaces. And furthermore, this stable subcategory, or not nuke 0, but rather just nuke of DC, is omega 1 compactly generated. And the omega 1 compact generators are exactly these basic nuclear objects. Okay, now let's just go back to this perfect complex story a bit. So recall that this is where we started. If you took just the algebraic derived category of a ring, that's an omega 0 compact, or in other words, a compactly generated category, and it's generated precisely by perfect complexes. So in other words, D of A is ind of perf of A. And what we have here is sort of similar. It's an omega 1 compactly generated category which sits inside the analytic derived category. So it's a reasonable idea to try to use nuclear objects in this analytic derived category in the same way that one uses perfect complexes inside the algebraic derived category. So one could use nuke C as input for K theory. But except this is not entirely correct, one would have to go a step further. And the reason why you can't immediately use this as input is that it is not necessarily a dualizable category. So, and that's what I'm going to talk about now. So let me leave this at almost. Okay. So now let's talk about rigidity. So rigid and dualizable categories. Okay. So now is where I invoke Efimov. So recall, this is due to Efimov. The classical context in which K theory or localizing invariance was studied was for small stable infinity categories. So a localizing invariant was a functor satisfying excision on small stable infinity categories. Okay, let me be concrete. Let's just say K theory and D is spectra. What Efimov showed was that there exists a unique extension of any localizing invariant to a larger class of categories where lots of analytic categories sit. And also a lot of categories from topology, such as sheaves of X and so on. So in other words, Efimov extended the domain of any localizing invariant. And that's called continuous K-theory. Okay, so now let me define these objects. Let C be a stable, presentable infinity category. Then we call C dualizable if the colimit functor from ind of C to C has a left adjoint. Or, well, equivalently put, a dualizable category is a retract of a compactly generated stable infinity category. And we call C rigid if it is dualizable with a closed symmetric monoidal structure has a compact unit object. And now the most operative part of this definition, such that compact morphisms agree with trace class maps. Okay, and this last part is where all the finiteness conditions are kind of hidden. So the fact that it has a compact unit object would tell you that trace class maps are compact, but it is rigid if these two classes of maps coincide. And in case you don't know what a compact map is, then a map is compact if for any map into some colimit, this composition factorizes through a finite stage. And yeah, so this is for all G. That's what a compact map is. And a trace class map is, so I previously mentioned trace class maps between Banach spaces as a map whose singular values are summable. But this is a more categorical notion. This says that home of the unit object mapping. So map is trace class if it lies in the image of this canonical map. Okay, so that's what a rigid category is. And now you might, well, it's sort of hard to verify whether something is rigid, but there is a recipe which takes as input any symmetric monoidal presentable stable infinity category and spits out one of these rigid categories. And that's due to Clausen. Of rigid categories. This is due to Dustin Clausen. So given something in PRL ST with a symmetric monoidal structure, and let's even say that the unit object is compact, but you don't need it for everything that I'm saying. Inside the ind of this category, we take certain colimits, and the colimits are of the following form. We take Q indexed colimits of x alpha to x beta, where J is just the map from C to in C, and x alpha and x beta are just some things in C. And you take colimits of the following form, where the transition maps are trace class in the sense that I just explained, the categorical notion of trace class. And this is the universal way to get a rigid category. That is, you get a canonical map from, well, okay, I didn't quite complete the description. So inside in C, you take these colimits and then take the colimits of these objects. So you take the co-completions of these things. Inside in C. Okay, and this whatever you get at the end of this process is called the rigidification. Sorry for being a bit sloppy. So in other words, you get a canonical functor, symmetric monoidal functor from the rigidification to the category you started with. And this satisfies the right universal property. But notice that the way I set this up as a kind of co-limit of trace class maps, this should remind you of more or less what I did with this nuclear bornology. So in this forcing of nuclearity, I started with some complete bornological vector space, which is just an inductive system of Banach spaces. And I equipped it with a further structure, which forced things to be co-limits of trace class maps. And one might therefore speculate what happens when C is the derived category of the complex numbers. And the answer is not that you get just all nuclear objects, but you need something slightly stronger. And the reason for that was because this is a Q-indexed colimit of trace class maps. But in the construction of nuclear bornological vector spaces, I had an N-indexed colimit of trace class maps. And there's a way to force this stronger property, and that goes as follows. So now let me call this forcing Q nuclearity. And what is Q nuclearity? I kind of make an obvious modification to this nuclear bornology. So I equip x bx inside C born of C with the bornology where I call S bounded in this Q nuclear bornology. Oops, let me. If and only if there exists a sequence of bounded subsets such that, and here's where the functional analysis part actually comes in. These transition maps are now forced to be trace class of order 0. And yeah, so if you don't know what order 0 means, then this is a condition which essentially forces this co-limit of over this inductive system to be a Q index co-limit. And that's equivalent to saying that any of these transition maps factorize through two other trace class maps. And that's what order 0 gives you. But more concretely, an order 0 trace class map is one whose singular values have rapid decay. So this means singular values have rapid decay. And this ends up implying that X with this Q nuke bornology is a Q indexed co-limit of trace class maps. Okay, and this is kind of the universal way to do this. So X with, okay, let me give this some name. Let me call this X rig very suggestively. So X rig to X is the canonical map or universal map from a Q nuclear bornological vector space to X. So part of the claim is that such a map exists and satisfies the universal property. That is, if I take something that is a Q nuclear bornological vector space, then it factorizes through this X ring. Okay, and moreover, this functor, which goes from C born C to C born C, is exact and again monoidal. So it descends to derived categories and actually factorizes through the rigidification. And this is just the inclusion of the derived category into the derived category. Okay, so that's what have we exactly done? We've described the rigidification of this analytic derived category in terms of a more well-known notion of nuclearity from functional analysis. So maybe to spell it out, this is exactly the incompletion of the stable infinity category generated by Q nuclear bornological vector spaces. Okay, so I guess I have like 3 minutes and I'll just end with some, well, this was a rather technical talk, so I'll just talk a bit about where I use these results and some applications and relations to the work of Efimov and Clausen and Schulze. So applications. So the first thing is I said I wanted to use this to develop a version of derived analytic geometry. And it turns out that this functor, which goes from the category of these overconvergent algebras or dagger algebras over the complex numbers, to cat infinity, which takes any a to modules but internal to the rigidification. This has all sorts of interesting descent properties. So this satisfies analytic descent. And well, so all this story was about the complex numbers, but you can develop this theory also over QP or ZP. So it turns out that for affinoid or dagger affinoid for this talk, let's say, which is defined very similarly over QP, this satisfies étale descent. But importantly, it turns out that over QP, this has a much simpler description. Namely, this rigidification just turns out to be the category of nuclear modules. And well, how does this relate to the work of Clausen and Schulze? So this nuclear category defined using bornological spaces. That is, I take the derived category of complete bornological QP vector spaces and take the subcategory of nuclear objects in that. That is exactly the same thing as the nuclear category of Clausen and Schulze. But, well, some details need to be figured out, but from more or less just talking to people who work with them, I got to know this. So this is this part I would say is still ongoing. This should be the same thing as the nuclear category of Clausen and Schulze. And there's also Efimov in the mix. So there's another category which is defined over ZP. It turns out that our nuclear category, that is, if we take the derived category of ZP and take the nuclear objects in that, this is up to non-commutative motives, the same thing as nuc tilde of ZP, which is the dualizable inverse limit of Z mod P to the N. And that's Efimov's nuke. And this is, as Efimov himself showed, is the same thing as the Clausen and Scholz nuclear category, which is defined using the derived category of solid ZP modules and then taking nuclear objects in that. So over ZP, it seems like all the nuclear categories just agree with this algebraic nuclear category. And well, kind of the whole point of all of this was that over any Banach ring, one can define this category of derived complete bornological R modules. And you can then take the rigidification of that. And if it so happens that your algebras over which you're doing analytic geometry are sitting inside this, so if A sits inside this, then mod A of D of R rig is the right input for continuous K theory. And this is part of this paper that I'm working on with Jack Kelly. Okay, and that's where I'd like to stop. Thank you for your attention.
Thank you, Devarshi. Can we all unmute ourselves and give the speaker a round of applause now?
Great.
Virtual claps. Any questions, anybody? Is there a bornological analog of solids?
Yeah, so solid would be let's say the QP and the ZP module completed version of condensed abelian groups. And the bornological analog would just be you just work over QP or ZP. So whatever I did, so I started with complete bornological complex vector spaces. I could have started with any base Banach ring like ZP or QP, and I could have like run through the same story.
Right.
So I would say that the key difference between the bornological and the condensed theory is that we don't have different theories for different Banach rings. So like fix any ring over which you want to do analytic geometry, and there is this category of complete objects, and there's precisely one tensor product, and it works in a uniform way.
Okay. And this paper is not on the archive yet, right?
No, it's almost on the archive.
Okay. And would you include the remark about the Clausen-Scholz connection in there?
Yeah. We've already put that in the introduction.
Oh, in the introduction.
Yeah.
Okay. Any other questions? It's a very interesting subject. There is a very big audience for this, who are probably at the intersection of, various other audiences.
Yeah.
Yeah.
For me, this I'll by the way stop sharing the screen so that.
Sure. Let me also stop recording.
Oh.